So the next thing I want to cover here is what's going on inside a transformer. So with we talked a little bit about the fact that it's going to be easier to transmit with AC at high voltage. And we also know that in any conductor that you're going to have a voltage drop automatically as you go from the power station down to the substation. And also, somewhat obviously, you don't want really high voltage in your house. It can cause fires if you get a spark. I mean, high potential somewhere, low potential somewhere. Energy is always trying to reach equilibrium. In fact, gosh, when I was at the University of Michigan, there was an electrician working there and actually died working on a breaker box just because there was just enough kind of dust in the air to start a plasma ball and burned him. Just burned him right to death. So it's not high voltage is not something to be taken lightly. So what we end up doing to sort of solve this voltage drop challenge or problem is build a transformer, and what you can see here are sort of this number 8 shaped chunk of metal. The metal is there really to contain the magnetic field. So just a couple slides ago, I was going out looking online for those donut-shaped objects. It's just a square donut. And the metal itself is going to be a better container, if you will, for the magnetic fields. The magnetic field lines want to stay inside that metal rather than just flying off into space. So again, here's your circle, your electric circle interacting with your magnetic donut. The input's here, the output's here. What's the math that tells us the proper design for this? Well, it's on page 323, box 9.2. Check it out. VP over VS, so that's your primary, equals NP over NS. So, for example, I think they might have it wrong. Well, for example, if you knew that your secondary voltage that you wanted to just say be 110, and your primary voltage, let's just say, was sitting at, we'll make it easy, 1100, you're going to need 10 times as many coils in your primary as you will in your secondary, straight from this VP over VS equals NP over NS. So simply by virtue of the number of coils in the transformer, you're going to be able to drop your voltage. And really, another way of thinking about it is that voltage is also dropping as it goes through these coils. So if you've got more coils in your output, the amount of voltage drop is going to be greater. If it was just a 1-to-1 ratio, you wouldn't have any. So hopefully that makes sense. Okay. Oops. Oh, no, there he is. Okay, so there's the man we've all been waiting for, Nikola Tesla. Serbian, started working with the entrepreneur George Westinghouse. You've probably heard that before. Also worked with Edison. They had their arguments about whether AC or DC was better. Tesla also had some very interesting experiments that he was doing just with the Earth itself as a conductor. Obviously when lightning strikes the planet, it goes into the Earth. So I wish I knew more about it, but pretty intriguing figure. Okay. Three-phase power. Why might you want three-phase power instead of just the single phase that we've been talking about so far? What's the big deal with that? Give me a.
You can regulate your electricity.
Well, it is a way of regulating the electricity. Here's the way I typically think about it. So, if we come down here, and everyone's ridden a bicycle before, right? So on a bicycle, here's one pedal, you're pushing down. Here's another pedal. Depending on whether you have cleats or not, maybe you can't actually pull up on it, right? So on a bicycle, your power, and when you're up here at the top, you can't really push at all. I mean, you can sort of push forward and backwards with a little bit of friction, but on a bicycle, your power curve is like, vroom, 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 with your left leg, and then it's doing something like this over here with your right leg, and you add the two together, and you get something, well, there's, let's just say, you got this much here, you got this much here, you're sort of peaking. You got something that kind of looks like this. It's not smooth. But what if you had many other people joining you slightly out of phase? It would smooth that out. It's the same exact thing with the AC power. So if we draw this guy at 0, we're going to draw the next one starting in at 120, so there's 90, here's 120. Let's just have him going up here, have him going down here, have him going up here, have him going down here, so something like this. And then we'll have the next one coming in at 240, so let's see, there's 180, there's 360, 240's heading up here, heading just after the peak down here, just after the peak up here, just after the peak, doing something like so. On average, you get a sort of a much smoother profile, and that's going to make sense, like on a lathe or a big drill, for example, where you're not getting the pulsing. And of course, you could add more phases, but 3 is just sort of the entry level. Let's get the job done number of phases. So. And there are other reasons as well, but that's the main reason that's apparent to me. So, and here's just a 3-phase generator, and rather than having the coil spin as we saw in the last one, you just got the magnet spinning. So it's relative motion. I don't know if I want to take the time to do it in class, but do take a look at that box 9.5. You've got your, I'll just make a note of it here in the notes. Box 9.5, we know that P equals IV. You can change that around and say that I equals P over voltage. So typically, you know what your bulb is, right? 100 watt, 10 watt, etc. This is what the rating is. And you know what the volts are. 110 or something. If you're doing DC, it's 12. That's going to tell you how much current is going to flow through your wire. You plug the thing in, and that's how much current's going to flow, no matter what. And then from there, you use your V equals IR. To tell you how much resistance runs through it. So you're going to know, you're going to need to know, how much resistance you need for a given bulb, you get a given power, so V over I equals R, which will basically say this is how much resistance is in that filament. I mean, every single light bulb, whether it's incandescent, neon, LED, in order for electrons flowing through it to turn into photons, there's got to be some kind of resistance. And that's more or less what you're calculating in this little box. So that's how the power equation and resistance equation are related. Okay, yeah, this is a long section. And so we're still on the distribution of power. So here's Sebastian Ziani de Ferranti looks on while testing his 10,000 volt cable in 1890. He's not looking all that, he's like, okay, you're gonna hit my hand here, or my hand's gonna hit the cable, but I hope nothing bad happens. Oh, that's his assistant.
Yeah, he's
That's right, his assistant. So if he were a more confident man, that would be him sitting there. His assistant is holding an uninsulated chisel and is driven through the metal casing of the live cable. So as long as his assistant is not grounded in an improper manner, he's going to be safe, just like a bird sitting on a wire or what have you. Okay. Talks a little bit about Niagara Falls. There's your 11,000 volts, making it 35 kilometers to Buffalo, then all the way up to 220 kilovolts, and then on to the national grid in the 1930s. And they talk a little bit about billing. The whole introduction of the kilowatt hour. Also talked about the rotating disc meters, which we still use to some extent. I have one on my house. And then tariff. I also talked a little bit about standing charge versus unit rate. That's still the case too, right? Right now, if you put PV on your house, you're still going to pay the so-called standing charge. That's just what utility has to make to maintain their grid. But then the unit rate based on how much you use. But if you make more electricity than you use in Montana, you can get that back. You're never going to make, for now you're not going to make money if you make more electricity than you use, but you're going to at least break even, at least down to that standing charge that I just mentioned.
That's insane. That you're not allowed to sell it back to the grid. Pennsylvania, you can.
Well, it might be a little bit of a head scratcher if you're a consumer, but if you are if you're a utility company and your primary shareholders are not your ratepayers, but the capitalists who have invested in the other bigger primary.
They want them to use as much electricity as possible.
Yeah. And I think another, reason that I've heard anyway is that if the systems on houses get too big, then they're just harder to manage. It actually makes the grid less stable. So I think they want to de-incentivize very large PV installations on residences for that reason. It's not an unsolvable problem, but it's something that just sort of adds to the complexity.
It's keeping Joe Schmo from going out and buying a bunch of stuff and putting it on his roof.
Pretty much.
Making the grid unstable.
Pretty much, yeah. So tungsten halogen, again, just another way of having a resistance. So this is tungsten. The halogen, of course, is the gas, one of the noble elements that's, so nothing catches on fire. So, it's essentially a vacuum in there. Fluorescent lighting, similar thing. Argon gas, phosphor coating, electrons floating through. The phosphor is just changing the frequency of the photons flying around inside so that it is more pleasant to look at. So modern incandescent, again, this is just kind of way, back to Edison. Halogen is B. Incandescent, we've seen those. And the compact fluorescent, right here is C, and then the LED, light emitting diode. So in this case, there's really no, I mean, the whole bulb itself is inside a glass enclosure, but there's no gas inside like you've got with the halogen or the incandescent, or the, fluorescent. Okay. Oh, one thing I do want to mention here while we're still on light bulbs is this whole notion of efficacy. Hey, we'll see you around time. I think this will be, I'm pretty sure there's a question like this on the exam too. It's efficacy rather than efficiency. So, and you can see that the efficacy are lumens per watt. So in the case of efficiency, we would be talking, watts out divided by watts in. That's efficiency. In the case of efficacy, you can think of it as miles per gallon, for example, is another kind of way to think of that. And in fact, Katie DeLessio was just looking for a solar-powered off-grid lamp to light our American flag out in front of the building. I guess law or tradition or convention states that you can't fly your flag at night unless it's lit. She was looking for something that had only 200 lumens, and I don't think that's enough.
That's not a lot at all.
Yeah.
That's a very crappy flashlight.
Yeah, so if we're looking at, I mean, even down here on page 991, low pressure sodium discharge lamp. I mean, maybe if you had the lamp way the heck up the
if it was close to the flag, but if you had it from the ground,
right.
It'd be, basically, like a deer spotting light, something.
Yeah.
1,000 lumens, 500 or so, but 200.
Yeah. So it's only the visible light. So you might have other photons coming up there. That's just what we can see. One candela. Okay, so a full sphere has a solid angle of 4 pi steradians. So a solid angle just, more or less means that instead of just a little slice of a pie, it's more like a cone shaped, and one sphere is 4 steradians. So a light source that uniformly radiates 1 candela has a luminous flux of 12.57 lumens.
Candela is just a candle power?
Yeah, it's...
like horsepower is, supposed to be it's 1.5.
Horsepower is physical process. Yeah, so this one's emits a monochromatic radiation frequency. So this is the hertz. So if you remember that funny little exercise we did where there were how many joules per photon, and that was based on the frequency. So you could actually take that number right there and turn it into the number of joules. So you could convert a candela into a watt rating, so this many watts per steradian. So anyway, kind of fun to think about. All right, well, I think we made it through 9.3. Let's just pick it up with 9.4 on Thursday. Oh, man.